there's like 2 points. I got over all of that and one, but those certain two, and I just was like, really. All right, look at your wallet, all the time. Not that expensive. Yeah, and you look at the true printing thing. I didn't even look at it, but I don't think we, I don't think we 30 minutes. Yep. Actually, maybe a little bit good. This next one, the whole one you guys, 30 minutes, forget you late after reading, and how it feels.
Welcome back, folks. We are now in week 15. This is closed week, but closed week is just code for final exam prep week. That's pretty much our goal this week. We're going to do a couple problems in section 10.2. I had a long comment here saying those problems are essentially just going to be a potential extra credit question on the real final exam. The extra credit's going to be substantial since, when you take a final exam and it's totally comprehensive like ours is going to be, it's kind of natural that you just sort of forget a topic in the moment of the exam itself. If that happens to you, a question from section 10.2, not the worst one, but a more routine kind of question, will be enough extra credit so it could be like a question swap essentially. Your grade can't exceed 100%, so if you solved all the questions and the extra credit question, then it's just extra insurance against any little simple mistake you might have made. So for this final exam week, I'm pretty much just taking questions all week after we get through our section 10.2 problems. We're not going to try to spend a ton of time in here, maybe about a half hour to 45 minutes is what we said. So any questions you might have throughout the course, whether it's a homework question, an old exam question, anything is on the table. I'd be happy to work through them. But I also have questions down here. I came prepared with about 30 questions I'll take a look into. So we'll probably start in this document as well after taking questions. Also, we're also looking into a whole bunch of extra credit opportunities. Let's run through these since we kind of just hinted at them before, but we didn't make a lot of comments. The first extra credit opportunity is really just a side effect of there being no late work policy on the syllabus. So that means if you missed a section, if you had a rough week, you're welcome to take a look at that section, complete the homework, and I'll accept it for full credit. Also, take a look at all your homeworks. If there was like a problem that you might have missed, it's natural. It happens over the course of an entire 15-semester week. If you forgot a problem on your homework, then I mark it in blue. And blue is just my way of saying you can go and solve that problem and submit it as well. I'll still accept a partial problem like that. Other extra credit opportunity we've mentioned, I think we posted this actually like right around midterm week after exam 2, something like that, is relative to the final exam. If you had like a off day, one of your exam scores are a little bit lower, maybe exam 2, your final exam comes back really strong, but I'll say you had the opportunity to relearn and master that topic. That's kind of the nature of what would have happened. And out of the sake of fairness, it's going to replace just the lowest exam score. It can't hurt you, so if you had an off day on the final exam, you're going to maintain your original exam scores. And this is the new one that was posted just today, but any questions so far? Okay, this one's weird because this should have been posted probably around the 14th of April. Our math department is really, really behind, just full disclosure on this one. They gave us a really short time on this opportunity right here for the course evaluation. And that's kind of bad because if you look into this course evaluation, it's like our boss's boss's boss, the State Board of Education, requires that this is done. So our math department could have been in some serious trouble not getting it out soon enough. So it's a requirement for every state college in Idaho that you all are not required, but you're allowed to evaluate the course. We can't force you to do anything, no matter what your instructor says, but you're allowed to have the opportunity to review the course. The document's right here. It could take on the lower end, maybe about 3 minutes if you rip through it. Totally up to you how you'd like to respond. It could take about 15 minutes if you're typing out full responses. So click on this. And after you submit all this, it is going to be anonymized, so that's kind of comforting. Take a screenshot. The page is just going to say, thank you for submitting your evaluation. Send that screenshot to my ISU email address, and I'll mark you down for the extra credit. It's substantial as well because we're asking you to do a lot in less than a 1 week turnaround. This closes on Friday, May 2nd, the whole thing for pretty much every class. So we couldn't extend this. Making it kind of nasty was not put in on time. But any questions with that last one that just came through? Okay, so there's something like 4 or 5 ways to get extra credit in this class, depending on how you're counting them. 10.2 extra credit question on the final exam. This will give you a percentage as extra credit since we're asking you again to do a lot in a short time frame. And also it's kind of appropriate to give extra credit like this on the final because it's at a really rough time. We do our class 7:30 to 8:37. That's already hard to learn at such a late hour. And now you're going to be doing the final exam from 8 to 10 p.m. I write the exam with that in mind. This is a rough, not ideal time for everyone. If it is just horrible for you and you feel like you really don't want to do it at that time, I made reservations to be in this same exact room, 5:30 p.m. to 7:30 p.m. as well. And you're welcome to just show up at that time slot. Doesn't hurt to email, but if you show up at that time, I'll give you the final exam. Just make sure I give you the right final exam since other students could be there, other classes could be mixed. I'll try my due diligence to make sure you get the right one. If you're in the online section, however, online section always works a little bit different. You'll have to schedule the final exam through the testing center, and they'll have to work with you on the schedule to make sure you can get in on a date. So Monday's the official day. If it fills up on Monday, then they'll have to push you to the next day. But any questions so far, folks, before we move on to the next part of the announcements today? Not a whole lot more announcements other than these are the same kind of sample final exams that we've been looking on all along, except this is now the entire course. All lecture notes are now just one big document as worksheets. Not meaning you need to solve all of these, but this is a way to target on a section by section basis problems for practice. That's also just a way for me to communicate that this is how I'm going to write the final exam. I take it out and set of questions, and I check it against these 2 documents primarily. I want to make sure it's a question that we did in class, and it's also a question that you did in the homework as well, that it aligns well. I don't mean the same exact question, but a very similar question, changed number, that kind of thing, slightly different function. These are the additional exercises. I do plan to post more documents down here if you just want another new look at some extra problems. This is also extra problems we'll be looking into in this class. After we do a little bit, hang on, no, that's the first sheet or the last sheet of the final exam. Definitely don't want to forget that comment. But really, this is just how exam 1, 2, and 3 has worked so far. It's all the same process. Think of the final exam as just exam 4 that happens to be 2 hours. I'm going to write it for really an hour-and-a-half exam with 30 minutes for just double checking your work and that kind of stuff. So this is the last page of the real final exam. It's going to be just really what I did is I went to the exam 1, 2, and 3 formula sheets and just started condensing. I couldn't bring every single bit of information in there, but this is the main stuff. So we have integration by parts, trig table for when it comes up, trigonometric substitution, and on down the line. So there's a good amount of stuff on there. But the major thing you want to do as a strategy for the final exam is have this available, either printed out or just on a tab somewhere. Orient yourself on where everything is at. And anything that's not on here that you notice you need as a formula, just write it down on a separate page, maybe make flashcards out of it. And that's going to get that information in your head memorized so you'll be well prepared. I think that's, again, the same exact comments we made on exams 1, 2, and 3. So we're now on this part of the course, just looking into a few more problems from section 10.2. But I'll turn it over to the class at this point. Any questions or problems or comments to start us out today? Okay, well, here's where we left off in section 10.2. We solved a tangent line problem, which is, kind of a nice callback from all the way back in Calculus 1. But the situation was weird. We're looking into parametrically defined functions. The formula is not bad, though. You just take the derivative, input the right information to get the slope, and then use your any format you'd like to solve for the equation of the line. But this is the new stuff in this section. If your curve is defined parametrically like this, where there's a function for the first coordinate, a whole function for the second coordinate, the derivative is the derivative of the y coordinate with respect to t, divided by the derivative of the x coordinate with respect to t. So we worked that out. We got 2 cosine 2t through the chain rule, cosine t in the denominator. And now this is our opportunity to come back to this problem and see, is that a real tangent line, y equals 1, or does it look appropriate on the graph? Here's our strategy, and on a real final exam, any one of these questions on the document, again, is going to be for extra credit. I'm also going to give the graph right here, so you can check your answer against the parametric plot to see if it's reasonable in the first place. So if you're working this out, we'd go sine t, sine 2t. We're going to go from 0 to 2 pi, but we want to put in on this location a parameter b to let it vary. From 0 to 2 pi, step size 0.01 should do the job. And so this is what the curve looks like. Plot this from 0 to 2 pi. It's sine on sine, and that's about what it looks like, just an interesting figure 8. We want to know the tangent line at a specific parameter, pi over 4. So we can check that by, let's put pi over 4 here just for reference. That was at about 0.78. So wind this back. This is like the parameter t sweeping out the curve as b moves forward. And at about 0.78, yeah, there's a horizontal tangent line right here. We respond with a horizontal tangent line at height 1. Let's just throw it on there for emphasis. Y equals 1. So that looks appropriate. But it had to occur at coordinates root 2 over 2, that's about 0.7 and 1. And here's 1. So yeah, that is about 0.7 right at height 1. It doesn't actually give me the coordinates here. The parametric plot kind of limits the functionality of this calculator. But now finally, tells us we have the right answer just by considering the plot. You'd have the opportunity to do that as well on the extra credit question. But that was the refresh of what we did last time. Any questions at all, folks? Getting through, well, looking into the graphics on this one. Okay, let's try this out again. There's 2 versions of this problem. This is the nice version where they just tell us, do it right at parameter value, pi over 4. Because that just gives us the coordinates immediately. We plug it into x1, y1, and we get those out. But if you reverse the problem, it suddenly becomes just a little bit more annoying. That's example 3. Hang on, we were on that thought. Let's do example 3 first. It can't hurt. While we're on that thought, let's finish this one out. Because example 2 is slightly different. We're doing things out of order, but you know, it's still the same math, either order we do it in. So same problem, find the equation of the tangent line, slightly different curve, but this time they gave us a point. We're doing it at 0, 2. That means the steps we have to take are slightly different. Let's first just throw in the graph to see what's going on. First coordinate is sine pi t, and that was kind of interesting in a way. Looks like one of those, could be a space filling kind of curve type of thing. This one is t squared plus t. And here's our curve. It's a weird one. As we move the parameter out, it comes through here and then seems to just increase a whole lot as b gets bigger and bigger. There's a little bit more to the story though, so let's find the parameter t relative to the point 0, 2. That's where we want to find our tangent c right there. We're expecting a negative slope and a line tangent at that spot. Now here's our sequence of steps if you're given a point rather than the parameter. Slightly nastier problem, but we can get through it. First thing I would do is just write out x is 0, y is 2. That gives us some work or some stuff we can work into the parameters. We can throw a 0 here, solve a trigonometric equation. Not everyone's favorite equation though, so let's try a 2 here first. Try the less complex one, that's a good strategy. Throw a 2 on this one, and you're solving quadratic. So if 2 is t squared plus t, standard method is get 0 on one side. Then factor. Factor correctly, there we go. Then use the zero product property. T has to be -2 or t has to be +1. Now that's weird, right? We want the point of tangency at 0, 2, and we have two candidates. The parameter is either -2 or +1. Sometimes you can eliminate one. So let's check it against this right here. It's an official check, so let's use this pen color. Recall, x takes on value 0 from the given point, so we're checking against 0 equals sine pi t, with the hope of eliminating a parameter value. But if you plug -2 in there, we get 0 equals sine -2 pi. And that is true. Sine at any multiple pi goes to 0. Plug in 1, well, same problem, right? T equals 1 gives us 0 equals sine pi, and that's true as well. So both parameter values work. That's kind of concerning. So we might want to look into this curve a little bit more, but if this was an exam question, all you have is a screenshot. So let's leave it just like that and maybe investigate a little bit further on what's going on, why there's two parameter values. But you know, the thing about these curves is they sometimes wind back on itself. Maybe power 2 is doing that. When we take on a negative value, it's converting back to positive. It's possibly retracing itself multiple times. We didn't see that if we start at a 0 value, but we might see it if we start off at a negative value. So let's say from -10, -10 as well. And now if we are starting off at a negative value, and this gets larger and larger and larger, hey, there it is finally. It comes down in that way. And if we started at, say, 0, here as well. Let's track this, what this parameter is doing next. At 0, it's moving up in that direction. So it went down with the negatives in that direction, and then at positives, it moves up. It's crossing over on itself, but that won't affect the tangent line. The tangent line is still the same, no matter what direction it's crossing through. So looks like we can use either value, and that's true in this problem. You have to be really careful with these kind of problems, because if it did this, though, this is the one we're really worried about. If it goes like this, and then maybe some other part of the curve comes through like this, now you have different tangents for sure. One of them is going to be a positive slope through this branch. The other one's going to be, let me try again, negative slope through this branch, and then a positive slope through that branch. So if our curve looked like that, there's two potential answers to this kind of question. But this one does have a unique answer, and it looks like any parameter value will work. We can try both just as a further check of consistency. At this stage, the problem starts off just like before. The next step is to just differentiate this curve. It's a dy dx. So we write in the derivative dy dx. That's not our normal derivative. Y is not a function of x explicitly. So we wind this back and say, by the methods above, it's dy dt. Divide by dx dt. And this step sometimes gets skipped a lot on exam settings because really you're just differentiating the y variable for the numerator, 2t plus 1. Differentiate the x variable for the denominator. By chain rule, this is pi cosine pi t. And now we have the structure for the slope at any parameter value whatsoever. Next step is to compute the slope. But again, you can do this two different ways. The slope m is dy dx. Evaluate it at either parameter value. If you're doing it once, that's the right choice, right? Let's just take it easy on ourselves. It is closed week. Take the one value. That would give us 3 in the numerator for t. Pi times cosine pi in the denominator. Cosine pi is -1, so this is -3/pi. And just as a check on consistency on this, making sure the diagram isn't lying to us, maybe if we zoom in a lot, the curves actually separate slightly, which could affect the slope. Let's see if we get the same thing at 1. So as a check, we calculate slope m again to be dy dx. Now at parameter value -2, the other possibility on this one, for plugging in -2, this is going to be -4 plus 1, -3 in the numerator. Down below it's pi, cosine. Well, cosine is an even function, so if it's -2 pi, that's the same as cosine 2 pi, no difference. Let's put it in this way, just slightly less confusing. But cosine at -2 pi is exactly +1. So the whole thing really is -3/pi. So wildly, it does check out. Both parameter values give you the same result. That's not true in general, just depends on what's going on with the curve. We're not going to throw in the weirdest kind of curves. It's going to be more routine where it just worked out because a curve backtracked on itself through the parameter value leading to that point. This stage, our work is basically done. Use any method for the slope of the equation or the equation for a line. I'll go y minus y1, slope m times x minus x1. The thing we had to calculate was that slope m through calculus, but now we just go back up here. So y minus 2 is slope m, -3/pi, times x minus 0. Have to love the zeros. I guess when you think about that, that's a y-intercept. We could have formed this equation a little bit faster. But we're here, so let's finish it off in this format. The equation of the tangent line has to be y equals -3/pi. And we did say a negative slope, so already that's something you could check on the exam paper with the diagram printed. +2. That'd be slightly harder to check, but you might be able to just plot that on there if you really want to look into it. For us, just to show in the class, we'll go y equals -3 pi. Oh, needs a variable, right? That looked concerning for a second, x plus 2. And yeah, that looks like it really is a good point of tangency. You have the best local linear approximation right around 2. This is always interesting to look into. This is so sensitive that if you go 3.141, that's a good approximation of pi, but not good enough. If you zoom in on that, you will see separations somewhere down the line. If you put in the wrong value, ever so slightly wrong, even in the thousandth place. Well, tens, hundreds, thousands, 10,000th place rather. But we've seen it two different ways. This is getting our tangent lines through. And just in case you want to practice these problems, I will put some practice problems down on the Moodle website right under here. So if you're targeting this as an extra credit question, I'll give you some problems to take a look at as a candidate. It can be a homework assignment since we're too short on time, so I'm going to post the solutions as well. And this is a good strategy as you're studying, just to get a feel for what in the world is going on. It doesn't have to be this utility, but any kind of plotting utility that can do parametric is a big help while you're learning this. Well, we'll try out a couple more problems along these lines. But any last questions, folks, on surviving this one? Okay, last problem, well, the next problem, the one we skipped, it's more about just thinking about what makes a horizontal tangent line or a vertical tangent line. But it's just more practice doing the first order derivative for this kind of equation. So let's solve a couple equations on this. We know we have a horizontal tangent line when, pretty much just for review from calculus 1, dy dx, what value would you all say it has to take on for horizontal? Exactly, a zero slope leads to the horizontal tangent, so 0 on this one. And now vertical, I don't know if this is covered too much usually in calculus 1, but we could definitely discuss it. Vertical tangent line is when dy dx I can't actually write down equals anything. We'll just have to say is undefined. Which makes sense, right? A vertical line is of the form x equals a number, and the slope for any line like that is totally undefined. So really, any way we look at this, first step is calculate dy dx. So let's do that above. Dy dx is the derivative of the y variable on top, so that's a 2t. Derivative of the x variable on the bottom, 3t squared minus 3. And then now we have a fraction. We're setting a fraction equal to 0 for a horizontal tangent line. And the only way that can pan out as true is if just the numerator is 0. So horizontal has everything to do with the numerator set to 0. And we're told this is going to happen at value t is 0 for the parameter. We want to find the actual point, so that's not our official answer. So we go back here and just form the point. So we'll say this occurs at xy equals, throw in the parameter value 0, and we'll have 0, -3 for that coordinate. This is the point at which you check that against the answer on the final or the graph on the final exam to see if it looks reasonable. And then we just do it all over again. Vertical means dy dx is undefined. This could be potentially impossible. If this was a plus, I'll fix that in a moment, then there's no way this is undefined. It's always defined because that's never 0 down below. And so we would just say none in that case. But if there's a minus, yeah, there's a way this is undefined. It's when the denominator comes out as 0 for the parameter. So we solve 3t squared minus 3 set equal to 0. It's kind of a nice structure, right? If you're looking into just horizontal or verticals, that's the process. Numerator set to 0 for horizontal, vertical set to 0 for, or denominator set to 0 for vertical. This one's pretty fast to solve. We'll add 3, divide by 3, so that t squared, or rather t itself, has to be either a +1 or a -1 to satisfy the situation on this one. So now we just take a look into what coordinates does that occur on. This occurs at, now we have a couple points, so let's just be specific how we are getting these. At parameter t is 1, we're throwing in 1 first. So this is going to give us a -2 for x coordinate and -2 for the y coordinate. So next one, at t equals -1. At -1 here, we have 3 minus 1, so coordinate +2. Squaring here gives us the same value, another -2. And so here's our claim. Horizontal tangent line, 0, -3. Vertical ones at these coordinates, always at height -2, just at opposite sides of 0. Well, any last questions, folks? Finalizing this one. Okay, this all comes together with the graph, so let's just take that extra time to see how it looks. Also because it supports the exam question like we've been mentioning. So let's plug this in at, for x coordinate, t cubed minus 3t. Let's wipe out that tangent line. And t squared minus 3 on that one. So let's increase b here. Doesn't look too good, but remember, I started at 0 from other plots, so let's throw in maybe a -10 here. That looks like a better plot, a little bit more accurate for us. Here's the moment of truth. We said horizontal at 0, -3, and that looks right. That's a horizontal at that coordinate. Here is +2, -2 for vertical, and another one at -2, -2 for vertical. So all these statements really checked against the curve. Well, there's lots of other things that we can take a look into when it comes to this kind of stuff. The other things on this list are concavity, area under a curve, length of a curve. Surface area of a curve we probably won't get into because that would wipe out the rest of our time. But those are the next ones we're going to take a look into. Any questions at all so far? Okay, and again, any one of these questions is bona fide a real extra credit exam question. This one's kind of nice because it's a little bit faster to get through. And the idea behind this one is it's all about the second order derivative. On example 4, we're going to look into concavity. Just to save some time, we won't plot this one, but we're just going to show what the method would look like getting through it analytically. Concavity is all about the second order derivative. So from calculus 1, we recall if the second derivative d2y dx2, if it's strictly greater than 0, not a greater than or equals to, but strictly positive, that will imply concave up. If it was negative, it would be concave down. Curiously, we're only looking for concave upwards on this one, so highly specific question. First step on this is we calculate the first order derivative, dy dx. And same familiar strategy, go to the y variable, differentiate it with respect to t. 3t squared minus 3 for the numerator. Then differentiate this x variable to get a 2t in the denominator. And we're halfway done, right? Now we need the second order derivative, and we'll be able to analyze that inequality there. So this is where the notes from above were kind of weird. It specified what the second derivative looks like. And this is what it looks like with a real example. d2y, excuse me, dx2 is d dt dx dt of, in the numerator, it's d dt of dy dx. Really ugly looking formula, but this is what it's really trying to say in essence. You put in whatever you had for dx dt straight out in the denominator, and that part's done. It's kind of weird in a way. Then you take whatever you had for dy dx, color coding kind of tough on this one, this whole thing, you just differentiate again. So d dt of 3t squared minus 3 over 2t. So that's not too bad to do. That's a quotient rule. We haven't done a whole lot of these, so it's a good review problem for that. Here's one way to analyze this, though. If you're dividing by 2t here, just to make the algebra a little bit more manageable, that's equivalent to multiplying by 1 over 2t. Then at this part, the fraction we formed, we'll hit this with the quotient rule. Take the derivative of the numerator, 6t, multiply it against the denominator, unscathed, just copied in. Then go minus, copy in the numerator, 3t squared minus 3. Multiply it by the derivative of the denominator, 2. Then divide by the denominator, 2t squared. And it naturally combines with that factor of 2t as well. So the next line, it's 2t cubed, or 8t cubed if you prefer. We want to simplify this as much as possible since we have to work with it algebraically to solve that concavity condition. So numerator is now 12t squared. We're distributing in a negative 2 onto that group. So this is going to be minus 6t squared plus 6. Simplifying to 6t squared plus 6 over 8t cubed. So kind of relaxing calculus again after surviving the last section of chapter 11. But any questions at all, folks, running through the derivatives? Okay, our ultimate goal here is determine that. So to get upwards concavity, which means we're solving an inequality next. The ways we do these are we look for critical numbers. There'll be one critical number where the second derivative itself equals 0. But based on that last problem, that's when the numerator is 0, and it's impossible. It takes a minimum value of positive 6 because of the power 2. There's another way to get a critical number. It happens when the derivative is just totally undefined outright. That's when the parameter value t is 0 on this one. We get undefined. So exactly one critical number. And it's at t equals 0, coming from setting 8t cubed equals 0, and it gives us that result. Does that make sense to folks on getting the critical number? Okay, at this point, the problem is pretty fast. We write down a number line, throw in whichever critical numbers you found. We found exactly 1. We're going to analyze the sign of the derivative. I usually do it in this kind of geometric form, but if you write out as a table, that's totally fine as well. And we're just plugging in values now. As a test value, throw in a -1 over here on the left range. It's going inside the second derivative, but we already know positive in the numerator. It'll be -8 in the denominator at a -1. So this tells us in this entire range, the left bracket, d2y dx2 is less than 0. Less than 0 means concave down in that entire interval. So we don't want concave, well, we would just say no values of t if it's concave down again. There's no concavity right at the 0 point, so we're checking on this next side. If we plug a 1 here, this is all positive. So we'll say yes at value 1, dy dx, d2y dx2 is greater than 0. So this implies concave up on that range. That means our work is basically done. We just want to say officially concave up on 0 infinity. But remember, this is for the parameter t itself. When the parameter t, it says which values of t is the curve concave up. We were solving this on a t-axis. So even though it feels like Calculus 1, there's some pretty big differences. Not a bad idea to write that down just for the emphasis, and to say for t here as well, just to emphasize it. So this one's not too bad. This could make a bona fide extra credit exam question as well. The major credit would be for getting up to the second derivative, and that would be the major thrust of the problem. And then just quick conclusion on concavity. Well, we've got a couple more to take a look at, but any questions so far? Okay, so another big thing that we do in Calculus 1 is find areas under curves. So this would be like chapters 5 and 6 in Calculus 1. And this actually ties in pretty well with our class, in the sense that to solve this problem, what you really need is u substitution out of nowhere. So here's the specification of the problem. If y is described as f of x, and we're wanting to find the area under the curve from a to b, we just integrate this way. This directly gives us area. However, we are going to parametrically describe both the x-coordinate and the y-coordinate in this way. And the claim is the area turns into that out of nowhere. It's not a bad formula to work with. It's just kind of a confusing formula to understand. It seems more complicated than necessary. But writing this down once makes it all clear. In fact, this is something that's kind of a common process in Calculus 3. You're going to get into things called line integrals. And this formula is kind of reminiscent of that sort of process. So we start by just writing area is the integral from a to b, y dx. But then we bring in the extra information of the problem. X is f of t, y is g of t, and sure explains that part, right? That's just a full substitution, y going to g of t. But here's the next magic of the problem. If it's dx here, and x equals f of t, here's a good tie-in. We can now take the differential of this whole equation right here. The differential goes dx equals the derivative of f at t. And because the variable is t, we throw in a dt. This is kind of like day 1 of this course. We had to do differentials just like these to derive integration by parts. But that dx can now be full on substituted for this value. We would have to change the limits of integration. So that could be some algebra right there. The alpha t goes from alpha to beta, but that's usually supplied in the problem to make the problem concrete. So we make a substitution here and we just say area is an integral from alpha to beta. Throw in the function for y. Y is defined as g of t parametrically. Then, using the differential, dx becomes f prime of t dt. And that's how we get the area under the curve for a parametric curve. Pretty weird, right? You just copy in the y-coordinate, the derivative of the x-coordinate, and you integrate with respect to t, meaning you have to use these bounds relative to the parameter. With all that in place, you could get the area under the curve. Let's try this out on our next problem then. Any questions first, folks, with that derivation? Okay, so here's our problem we're going to try this out under. This is a good problem where we want to plot this first. So let's give a plot for this so we can see if this is even reasonable. Then we'll use this formula down below. So we're going from 1 to 9 on x. We could solve for parameter values for that, but let's just look at the curve itself. Oh, t cubed plus 1 and 2t minus t squared. So here's our curve. Looks like I have a big enough range to specify this. X is going from 1 to t. It's 1 right here, 1 to 9 rather. It's 9 right here. So finding the area of the curve is finding that area. So it does match up to a calculus 1 problem in that way. Let me show the controls again. If you decide to try this out and plot these things yourself. So here's what our problem looks like. And our goal is to find this area right here. So it's enclosed by the x-axis and this parametrically described curve that we plotted. But I think this is kind of a fun problem. Honestly, I think sometimes the tangent line equations are a little bit tougher on this. Here you just say area is going to be the integral from, hang on, here's where we have a snag, right? You do need those parameter values. So let's start off finding those values before we just launch into an integral we can't compute exactly. It's not too bad though, because if x is from 1 to 9, you're just putting it right in here and immediately getting parameter values. So if x equals 1, this implies 1 equals t cubed plus 1. Subtract 1 from both sides. This means t has to be 0 as a parameter value. The only way to make that true. Plug in 9 for the next one. X is 9 implies 9 over here is t cubed plus 1. Subtract for 8 is t cubed. Cube root is going to give us a 2 value. So now we have the right parameter values. We're going from a 0 to a 2. Let me fix that cube though. Does that make sense to folks on getting the alpha beta part? Okay, once we have alpha beta, we just bring it all together. So here's the formula right above. And this is going to be area is going to be an integral from 0 to 2. The formula says, put in the g of t function. That's what y is specified as, 2t minus t squared. So word lets me grab that pen. There we go. 2t minus t squared. Then for the next factor, you take the derivative of x. So this is dx dt. You could also call it f prime of t in Newton's notation, and it just goes right inside there. So that's just a 3t squared dt. So now we've converted a problem that looks pretty mysterious and difficult to compute on to just that. It's now bona fide a calculus 1 problem. It only just looks odd because the parameter t rather than a variable x. So let's run through this, integrate from 0 to 2. Distribute first to get 6t cubed minus 3t power 4. Then just take antiderivative at this point. So we have 6/4, so 3/2 t power 4. Let me double check that. That looks about right. Minus 3/5 t power 5 from 0 to 2. The 0 is nice there. We can just say 3/2 times 2 power 4 minus 3/5 times 2 power 5 minus 0. So this is turning into a derivation through or a long arithmetic problem. Let's just wipe it out on the calculator right here. In the exam setting, I'd say this is definitely appropriate. You've got an exact answer down. We're just going to see if this is reasonable by computing it. 3/2 2 power 4. The only reason we're not too worried about doing the arithmetic today is not just because we're trying to review, also because on a real exam, if you focused on the calculus elements and just rip through the arithmetic, that's the right way to go for it. The major credit is on the calculus itself. We get a 4.8. And so that's our official answer, exactly 4.8 units squared for that area there. Well, any last questions, folks, finding the area? Okay, at this point, we're now looking into the length of a curve. This one is a good one to do as well because we look into lengths of curves as well in this class. So this one has a good tie-in for a real review problem. Only difference is we're going to do it parametrically. So we're going to use our old equation from chapter 8, the length of a curve. I think it's section 8.1, and just see how this goes parametrically. It's really the same kind of ideas as what we did over here. We just change variables, do a little bit of algebra, and we get a new function or a new formula. So here's how it goes. The length of a curve from alpha to beta, when the curve is described parametrically, is that. But the tie-in from our actual work goes like this. If y equals f of x from x equals a to x equals b has f prime of x continuous, we needed the mean value theorem on our derivation of this one, and that was a condition we also needed to integrate this. We can say with that property, the length of the curve is going to be integrate from a to b, square root of 1 plus dy dx squared dx, and that's the whole formula. Here, looks pretty similar, right? It's dy dt though, and dx dt. Same kind of idea is going to allow us to get that though. We take the differential of this, do some really weird algebra, and multiply this dx by the new thing, distribute it in, and we get that formula below. That's the hand-wavy way to say it. I'll leave this up to the class though. Should we try for one more derivation, or should we launch into the problem? Totally your choice this time. Good call. Let's go into the problem. You kind of have a really good idea how it goes. It's basically this again. You do a dx and you just work it into the problem. Let's go right into the problem. We've got a good formula here, and here's how this one will go. Well, this one was the application problem in this section. I don't know if the curve specification makes any sense in this context, but the fun part is the units actually do. At least that's what ChatGPT told me. I'll have to look into that a little bit more closely to be really, really sure about that. It tells us the position of a high energy proton in the Large Hadron Collider, something built in CERN in Europe that collides particles like protons to look into other elementary particles. The proton is going to be described parametrically in this way, and we're only looking from t going from 0 to 1 in this time measurement, femtoseconds. So everything is happening really, really fast, and distances are very, very tiny. Yet, this might be an interesting problem to solve in certain contexts. How much distance did this proton actually travel from 0 to 1 femtoseconds is our question to resolve. And actually, it's a pretty fast one to resolve by this formula. What we would do is go length equals We already have the alpha beta provide for us. So unlike the last problem, we can launch right into this. Going from 0 to 1 with those specific units. This is a dt problem. And we just go dx dt squared really fast, right? Derivative of this x is 4t, and it has to be squared. So that's this part written in, giving us that result. Then plus dy dt squared, same idea. Take the derivative, square the result. Derivative on that one is a 9t squared. And well, just like what we discovered in chapter 8, though, once you get it down on paper, it's another thing to integrate it, right? So let's work out algebraically, what is this? This is the square root of 16 t squared plus 81 t power 4. We need to integrate this integrand. So not a whole lot of simplification, but you can factor out t squared like this. Root t squared, there's the power, leaves behind 16 plus 81 t squared. And common issue we always need to think about algebraically is how the root of a squared is the absolute value of a. But the problem is rigged this time. The value for t is only positive. So even if you put absolute value t here, you did your due diligence, but then it just simplifies right out. It's worth mentioning because that part of algebra sometimes is just like totally ignored, and it's a surprise when it doesn't work out. But we just get t root 16 plus 81t squared. And you know that's not a bad integral. It's a little bit annoying because we need a u substitution, but nothing we can't handle. So let's put this all together. The length is now integrate from 0 to 1, t root 16 plus 81 t squared dt. So next, let's do the sensible u substitution, which would be inside of that square root. U should be 16 plus 81 t squared. So now the differential is 162 t dt. We've got the t dt right here. We just want to divide by 162, or you could do that in your head, I suppose. Let's write it in on paper. 162 du is t dt. So this is the swap we're going to make. But maybe another thing we should do is change limits of integration as well. So if we have u as this variable, and we have t going from 0 to 1, gives us new bounds on the variable u. U is going to be going from 16 to 97 on this one. So now the u substitution is fully specified. Throw in these new bounds. Following the same exact order, 16 to 97. We get, in place of the square root, I'll write power 1/2. 16 plus 81t squared is just u. And now dt, well, t dt is 1 over 100, 162 du. So it's all on paper. Now we have a pretty nice integral to get through. The length here is going to be 1 over 162. Antiderivative on u is going to give us u power 3/2. So times 2/3. Integrate or evaluate rather from 16 to 97 on that antiderivative. Does that look right to folks so far? Kind of simplifies over here, but you know, if this was an exam problem, and it's going to be like the last problem on the exam is an extra credit problem, if it is this one, you probably just want to kind of move through this really a little bit faster. Let's do that same strategy. I would, if doing this in an exam setting, write in length is 2. I mean, it does simplify, but let's just leave it. 3 times 162. 97 power 3/2 minus 16 power 3/2. And I'd probably just approximate it to see how reasonable the number seems. I don't know if I'd have any great intuition of how reasonable it is. I mean, these are strange units, but let's do that regardless and see what we get. So 2 divided by 3 by 162. 97 power 3 halves. My 16 power 3 halves. Gives us about 3.67 femtometers. And we did it, folks. That's finding the length of the curve. In the reading, they specify how you can do even more than this. You can use these methods to say, how fast was this going in femtoseconds per femtometers, that kind of thing. And a whole bunch of other stuff, but we settled for just doing the length on this one. Any last questions at all, folks? Surviving that last problem here. Okay, so as far as the extra credit question goes, it's going to be one of these. And any progress you make along these lines is going to indicate to me you studied the parametric curve section. So I'm going to be pretty generous with the extra credit. I'm going to be posting below here some sample problems and the solutions to further support any kind of studying in that direction. If you decide to go straight for the final exam questions and really just focus here, that's another equally valid strategy as well. But I guess we're done with this section. Any last questions or comments before we convert over to reviewing? Okay, let's switch out documents then. We're now in section, well, that's what I would usually say. We're now in the final exam review for the whole course. Congratulations on getting there. It's a brutal 4-credit course for the semester. It's been a long 15 weeks, but we're nearly there. Here's what my final exam review questions look like. Essentially, I've just taken a huge random selection of problems on a section-by-section basis, not including sections 10.1 or 10.2, since we didn't get too far into that chapter. And so it starts off with just lots of integration. This is chapter 7. Moves through some applications, sequences and series, but it's kind of mixed up and out of order. Sometimes we'll hit some blocks that look like this, concept questions. Hey, there's some parametric stuff. I guess I lied a little bit about that. And then sure enough, you're back to sequences and series. So this document is kind of all over the place. But the idea for this document is any question that you bring to class on Wednesday or Thursday at the start of class, I'll include on this document. So if you have questions you'd like to ask and have resolved, I'm happy to make those additions to these documents. And if you'd like, you can just email me before class. You can just send them by email, and I'll include them as well before class starts. But without any questions so far, let's just go from one down the line. One thing we want to put on this document, though, just as some really good emphasis, you definitely want to review with this sheet available. So we'll call this information and just cite it into the document as we use it. But here we are. At this point in the document, we're pretending we're all the way back in section 7.1 or chapter 7. This is kind of all over the place in chapter 7. If you're in chapter 7, the things you're probably going to want is some basic information on these integrals here. These are integrals I'll never ask you to derive. If they come up in problems, you're totally welcome to cite. So that's why they'll be on that document on the final exam. Method here is going to be integration by parts, but here's the review on that. We write out to u equals dv equals, and we get started by doing the acronym LIATE. The recall on that in section 7.1 notes is this is a logarithmic function, an inverse function, algebraic, trigonometric, exponential function. Anyone see what x should be based off that? Good call, absolutely. It's this a part right here. By algebraic, we mean like x squared, x cubed minus 4, anything like that is a really good choice for you. If you're not a fan of acronyms like these, this is kind of a vague one, just random letters of the alphabet. The thought here is whatever you pick as u should have a reduction of complexity at minimum when you go define its differential. And that is what happens. The differential here is just 1 dx. If we put cosecant squared in here, It gets more complicated because now it's a chain rule problem. We're doing no favors to ourselves. So that means everything else, including dx, goes into the differential on this line. So cosecant squared x dx means we need an antiderivative. That antiderivative is not guaranteed to be on this list. We have to know some of these antiderivatives to get through the problem. Anyone happen to know which one it should be? Close. This one's a cotangent. We'll have to throw in a negative sign because of the derivative giving us another negative, but absolutely. And let's say this is a real final exam and you just blank that and you did put tangent there. You might lose a point, but if you're doing the rest of integration by parts correctly, based off your chart over here, you're going to get a lot of the partial credit because that's the thrust of this question, the method of integration by parts itself. But this gets us started. The formula goes uv minus the integral v du. With that in place, correctly put in place, we're just putting in a whole bunch of substitutions. X for u, negative cotangent x for v, minus the integral of v, another negative cotangent x, times du, that's just a 1 times dx, so we'll throw in a dx there. Got a negative sign, let me include that. That negative sign there, no harm in going plus plus, saving a step algebraically. Hang on, my document here is fighting me. There we go. So we need an antiderivative of cotangent x. We did the antiderivative of secant x as a derivation, and I'll provide both of them because, again, these are some non-standard derivatives or antiderivatives. Solving this one is like a problem unto itself. So cite the table, and we have negative x cotangent x plus the natural logarithm of cosecant x minus cotangent x plus a constant. And then that problem ends right at that step. Again, if you make a mistake here, I track your mistakes and just see how the algebra and the calculus goes. If everything else was correct on paper, you get the right, most of the partial credit. Yeah, go ahead. Uh-oh, so that should have been, oh, gotcha. So cosecant, oh, looks like I'm a little, oh, I'm looking at that one. It should have been that, I gotcha. So antiderivative of cotangent, thanks for spotting that one. I guess I was just really excited to use that nice formula above. Should have been that one down below there. So natural log sine x plus constant. Thanks for spotting that weird omission there. Not too sure why I was thinking cosecant, just looked like it, I guess, bad penmanship or something. But other questions so far? Okay, one down. We've got 5 minutes. I think we could do that in 5 minutes. What do you all think? It's a u substitution. What do you think we ought to use for the u on this one? Any volunteers? Tangent's a good call because the differential is a secant squared. We'll split off 2 powers of secant, leaving an even power. And yeah, that's a good call. This will work on this one. So u tangent x now means the differential is secant squared x dx. Now here's the strategy from this point. Start reorganizing the integrand itself. Tangent squared x looks great because this whole thing is going to be a u squared officially. Then we go secant squared times secant squared x dx. And this part's good because that's going to give us the du as a full swap. The only thing we're worried about is secant squared x. But also notice, I didn't copy it in here, you do have some great identities provided by the trigonometric substitution table. So use this one. Secant squared is just tangent squared plus 1. So take the odd part out that doesn't have anything to go with it. It's tangent squared plus 1. But that means it's u squared plus 1 through this u substitution right here. Then we just bring it all together. This is turning into u squared from the first part times u squared plus 1 from secant squared x. And then we don't really want a times there, just a du from the differential part right here. Once we get to here, we're basically home free. So this becomes integrate u power 4 plus u squared du. The antiderivatives are 1/5. And you would write u power 5 here. But then you have to undo that substitution. It's really tangent power 5. If you took that shortcut, that'd be a fine step to take, I'd say. But it makes the notes confusing. So let's take one additional step. Here's the antiderivative, and then it becomes 1/5 tangent power 5x plus 1/3 tangent power 3x plus a constant. That stage, our work is done. It's a hard one to check by differentiating because sometimes you have to use a lot of identities to check it out. So it's a good one to just be really certain you're doing well in the forward process. That's the faster check. But any last questions, folks, surviving this one? Okay, this is probably a good stopping point for us. I don't think we want to try one in a minute and a half. That's really pushing it. But again, we're just going to go through this document. If there's burning questions you'd like to bring to class, I'll be happy to include them. So don't hesitate to email or just ask at the start of class. But have a great evening, folks. We'll pick this up right here next time.